Good morning, student. Welcome to a new platform of learning. It has been a long time that we have not met, but thanks to technology that we have to meet through this medium of teaching. Last time we ended with a connection of cells in series and in parallel, and we are simply going with the continuation. I believe that at this point in time, you can calculate cells in series. I can also calculate the resultant EMF in parallel. Today we are moving forward with what we are going to call Ohm's law. I know you must have read about Ohm's law in a textbook, in your exercise book. But today we are going to elaborate on that. You ask yourself, what is Ohm's law? We start by defining Ohm's law as is a current that flows in a conductor which is directly proportional to the potential difference across its ends. It means that the higher the current flow, the higher the PD across the ends of the wire. Therefore, a material that obeys Ohm's law should have a straight line graph, because increase in current leads to increase in potential difference. There are two types of material here. We have the ohmic conductor and non-ohmic conductor. When you talk of ohmic conductor, this is a conductor that obeys Ohm's law. For example, metal. Example of a metal, we talk of a copper wire, we talk of aluminium, we talk of mercury. And therefore, these materials obeys Ohm's law. The current voltage graph is always straight. It's a straight line. And when you calculate the gradient will give us the resistance of the wire. And we have the other part known as non-ohmic conductors. These are conductors that doesn't obey Ohm's law. Example, we talk of graphite, we talk of semiconductors, we talk of diodes. With these conductors, the current voltage graph is not a straight line, it's a curve. And therefore, the straight line, you can never calculate the gradient as that in a straight line graph. A point will always be given to you to enable you to calculate the gradient of the graph at that particular point. We have an exercise on the board to demonstrate what Ohm's law is all about. Look at the exercise on the board. It says, a student carried out an investigation and the following results were obtained. Here we have the voltage in volt, we have the current in amperes. These are the values recorded by the voltmeter, and these are the values recorded by the ammeter. These values was gotten through an experimental action or process. Here, the question demands, draw a graph of voltage on the y-axis against current on the x-axis. I know drawing a graph is not strange because we did graph work in nuclear physics. Okay, the first thing you have to draw your axis. We have the x-axis known as the horizontal axis. It carries the current measured in amperes. We have the y-axis, which is labeled the voltage measured in volt. Here you are going to calibrate your axis. The y-axis is going to carry the voltage from 0 up to 8. Therefore, we take interval of 1. You don't just go and pick this value and plot on the graph. You take an equal interval of scale. For example, the minimum or the smallest value is 0 and the highest value is 8. And therefore, we need at least 8 spaces to plot our graph. That is why I put 1, 2, 3, 4, 5, 6, 7, 8. You have not seen 1.6. You have not seen 3.2. You have not seen 4.8. But I can trace out 3.2 from this point. For example, 3.2, this is 3. Normally this 3.5, therefore 3.2 should be somewhere here. Therefore, all these values 4.8, 3.2, 1.6 can be traced on this graph. And if you look carefully, you have equal interval from 0 to 1, the difference is 1. From 1 to 2, the difference is 1. From 2 to 3, the difference is 1. And therefore, your scale must be equal. If you go to the x-axis, we have the current measured in amperes. The minimum value is 0 and the highest value is 1.0. The same thing applies on the x-axis. You cannot just pick these values and you plot on the x-axis. We need equal interval. For example, we can take 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, which is a maximum value. At this point in time, the values are of equal interval. From here, we cannot plot our graph. We have 0, 0. 0, 0 means that the graph is starting from the origin. And this is the origin, 0, 0. That is 0, 0. We move again. When the voltage is 1.0, the current flow is 0.12. Voltage 1.0, this voltage here 1.0. You take here this 1.0, if you have to, you take a line, you go like this 1.0. The ammeter is 0.1 to this 0.1. 0.1 to this 0.125 is a middle position. Therefore 0.12 should be somewhere around here. Whereby if you bring this value up, and this one going like this, you are going to meet somewhere here. And you put an X. The next value we have 1.6. 1.6, you cannot find 1.6, but you can identify or you can trace our 1.6 from the y-axis. This is 1. This is 1.5. Therefore 1.6 is just immediately above 1.5, somewhere here. Therefore you go like this. And then it's again 0.2. This is 0.2. Going up, they are going to meet at this point. You take them at the next value, you have 3.2 and 0.4. And you keep on plotting like that. From this plotting, you realize